For this video, I wanted to go over pulmonary ventilation rates as well as alveolar ventilation rates. So pulmonary ventilation rate is based on how many breaths per minute you have. So if I timed myself and had, normally you can breathe in and out 12 times per minute, and that's going to be multiplied times the tidal volume. And that's just the air that is moving in and out of your lungs. It's not the maximum volume, it's not the minimum volume, but what your lung in a relaxed state will hold. So that's how we find pulmonary ventilation. And then there's another thing we have to take into consideration is anatomical dead space, which is air in the bronchi, bronchioles, etc. that's not oxygenated. It's just kind of like, it's just space, right? Then there's physiologic dead space, where you have alveolar and anatomical dead space. So there's unoxygenated air in the alveoli as well as in your bronchi. That's what we call physiologic dead space. If we scroll over here, we can see these are three alveoli. Well, this is one alveoli, and it's going through the process of inhalation and exhalation. And throughout this process, we can see in the blue shaded portions, we'll have oxygenated air, and in these white portions of the alveoli, we have dead space, or just air that's not oxygenated. So when we inhale, if we think of this kind of like a plunger, it goes up and down and gets absorbed, or oxygen will get absorbed as the plunger goes down, and then as the plunger goes up, the air moves out, so it can't be absorbed. So we see that with inhalation, we push air into the alveoli. We have 150 millimeters of mercury of a pressure of dead space from what was already in the bronchiole, right? And that's pushed into the alveoli. And then as this 350 sits here within the alveoli in a space where oxygen can be, where it can diffuse across the membrane, it depletes. And then we're left with this, where we have complete dead space in the alveoli. And in the bronchiole, we have 150 millimeters of mercury of pressure of oxygen that's just not being used. And so that kind of sits there. And then as we exhale, we push this dead space up into the bronchiole, moving the oxygenated air up as well as the used up air. And then the process restarts, and we get inhalation, where the plunger goes down, we reoxygenate air, it's used up, and the cycle continues. So to determine alveolar ventilation, which is different from pulmonary ventilation, we have to take into consideration our ventilation rate, which is breaths per minute, and the fresh air that we're getting. So if we have a ventilation, or if we have a fresh air pressure of 350 of oxygen when we inhale, and that gets depleted with each breath per minute, we'll get 350. So we would multiply. So if we had 12 breaths per minute, then we would have 350 millimeters of mercury, or milliliters. Sorry, I've been saying that wrong the whole time. Yeah, well, actually, I think it's a pressure. Millimeters of mercury over here. If we multiply those two, then we'll have a total of 12 times 350. Sorry, I forgot to multiply this out. 10, 7, 350. That's going to come out to 4,200 millimeters of mercury of fresh air that was able to be absorbed within that minute because of our breathing rate. So what does this tell you if we have faster breathing rates or slower breathing rates? Well, if we increase the time that this fresh air gets to spend in the alveolus, then more is going to be absorbed. So slow, deep breaths are going to increase this number and increase the amount of fresh air that enters into the alveolus. In contrast, if we have rapid breathing and shallow breaths, we're not going to be pushing as much fresh air into the alveolus, and therefore we will not have as much of a pressure buildup of oxygen that can diffuse across the membrane. And so that sums up alveolar ventilation as well as pulmonary ventilation rates, as well as why slow, deep breathing is more beneficial than shallow, rapid breaths. It's because you get more oxygen into the system, both by volume and by diffusion rate across the membrane.